Okay. Well, let's go ahead and get rolling for today. So, announcements. If you walked in a little bit late before I made this announcement, make sure you get your problem sets in. That way, if I start answering questions on it during the review, right, then you don't get an unfair advantage. So make sure you turn that in. Secondly, I will post a key, or there will be a key that will be posted on this right after class today. It'll be posted an announcement on Canvas. So, talking to the TAs, they have lots of things going on as well. So we're not going to get this graded before Monday, for sure, before the exam. So you won't get that kind of feedback, but I wanted to go ahead and give you the key so you can look at that and use that as a studying tool, at least look at the right answer for that. Okay, we'll try and get those grades back to you midweek next week, okay? So that's that. Also, after class, I'm pretty much got to book it out of here, so I'm not going to be able to hang around and answer questions. I got a parent-teacher conference that I got to get to right at 3:30, so I got to leave pretty much right away, okay? All right, so as far as what we're going to do today, so I want to do, like I said, I want to do a little bit of mop-up. I want to go real quickly back into gluconeogenesis, look at something, and then I'll just kind of open the floor up for questions. So hopefully you have some questions. Of course, we have our exam on this Monday. Okay, that's the big thing going on next week. That's the only thing really due next week, our exam. Okay? All right, so what goes up and down at the same time but doesn't move? A merry-go-round. No, but that's moving. I like, like going like this. It's true. It doesn't move laterally. It's going around. What? Anyway, there's actually one in this room. A staircase. Exactly right. A staircase. Right. All right. Staircase. Okay, so let me go ahead and do this. I'm calling it mop-up. It's not really mop-up. I wanted to add something essentially to gluconeogenesis, and I think this is actually a good way to kick off into a review session. We talked a little bit about gluconeogenesis. We looked at the need for it. We talked about the fact that glucose would have to be supplied to the bloodstream anywhere between 3 to 4 hours after a meal. And that glycogen would be a very important part of that. We'll get to glycogen metabolism later on. Gluconeogenesis, as that fast progresses, will become more and more important in terms of excreting glucose into the bloodstream to ensure that glucose levels remain high. So to kind of connect that topic with the topic that we've talked about earlier in lecture 2, absorption of glucose, I wanted to go ahead and draw out this graph, okay? So what I'm going to draw out here would be a velocity graph, okay, of the transporter GLUT3. So we talked about GLUT2, we talked about GLUT4 in lecture 2, and we talked about some of their specific kinetic properties, in particular GLUT2 having that really high KT, where GLUT4 pretty low KT but not found on the membrane unless insulin's present. GLUT3 has the lowest KT of all of those if you look on that list, and it's found enriched in neuronal tissue. And so I wanted to go ahead and do this. So if we call this, let's be kind of careful how I draw this, but let's say this is our Vmax. Let's do this. All right, so this GLUT transporter is going to look something like this in terms of its hyperbolic saturation profile, okay? If we do this, I may have been a little bit too extreme on this, but let's call this half Vmax. Okay, which means that if I draw that over, drop this here, down here, this would be my KT or KM, that's fine either way. And the KT for GLUT3, I'll go ahead and label this up here, GLUT3, is about 1.5 millimolar. Okay, that's its KT. It's about an order of magnitude, or about 10 times smaller than the KT, KT of GLUT4 or GLUT2. Okay? Now, here's what's interesting about this. I'm going to go ahead and draw this. Let's just go ahead and say that this, somewhere about here, would be about the lowest concentration that you would find of glucose in the bloodstream, about 4 millimolar. About twice that would be 8 millimolar, and that would be about the highest concentration of glucose you see in the bloodstream. So if I were to draw this up here, all the way up to here, intersect that with the y-axis, draw this here, okay, intersect that with the y-axis. You'll notice here that when I have a twofold drop or twofold increase in the concentration of blood or concentration of glucose in the blood, going from 4 millimolar to 8 millimolar or to 8 millimolar to 4 millimolar, I have a pretty small change in the absorption rate of glucose in the neuronal tissue based off of these kinetics. Okay? Now, here's what's interesting about that. If I were to go down, okay, it's a little bit more than 2.5, but I just want to show you this, okay, or a little bit more than twofold, so about twofold change. In the direction below 4 millimolar, notice what happens in terms of my change in rate of glucose absorption. Because of where we are in the curve, it's going to significantly drop, much more significant than here. Now, this is exaggerated. Okay, we could demonstrate this mathematically too. This is a little bit exaggerated based off the way I've drawn the curve. But what I'm trying to illustrate to you is this, that one of the reasons that blood glucose concentration needs to remain above 4 millimolar, okay, around 4 millimolar, is because as you start to drop lower than that, the kinetic properties of the GLUT transporter in the brain in particular, right, you really start to lose the capacity to absorb glucose into the brain. Not only that, but of course the brain is consistently using glucose. And if it starts to run out of glucose, then it's in trouble. Okay. Now again, these numbers are a little bit exaggerated, but I wanted to go ahead and at least show this graphically, okay, in that regard. That's my mop-up of this, okay? So still kind of on the need end of this. Why is it important to keep glucose in the blood above 4 millimolar? There are lots of reasons. This is one of them. Okay, right. And that's it. That's all I wanted to say. I think that everything else that we've talked about with gluconeogenesis, we ended here on Friday. We ended with this on Friday. Pretty much everything that we wanted to say beyond that, I don't think I need to say much more. I will just kind of, because I said this at the very end of class, and I said it fairly rapidly, going back to this glucose 6-phosphatase reaction here, okay, that enzyme is expressed primarily in hexokinase, or I'm sorry, not hexokinase, but primarily in the liver tissue, primarily in the kidney tissue, and also the small intestine. But the gene itself, okay, is found embedded in the membrane of the smooth ER. Okay, I had a question about that after class. It's a smooth ER that you're looking at here. Okay, and then there's these transporters, a glucose 6-phosphate transporter that gets glucose into the lumen of the ER. That is converted to glucose, takes the phosphate off of it, glucose 6-phosphatase. Glucose is transported back out into the cytosol, and this is transported out into the cytosol, and then glucose can be transported out into the bloodstream. Now, I had an interesting conversation with an individual after class too, and the question is, well, why do that? Okay, why would we move glucose into this environment, the ER? And the thought was, the student brought up was, well, is that because you need that the ER is responsible for glycosylating proteins, which is an interesting thought. That is where the primary glycosylation events of proteins occurs, which means that you need glucose in that environment. Right? So this is one potential mechanism for getting glucose into that environment. I'm not sure that's why glucose 6-phosphatase is there. Could be. Okay. The other aspect of this would be maybe a regulatory mechanism. So hexokinase catalyzes a trapping reaction in the cytosol of these cells. Okay. It might make sense that then glucose 6-phosphatase would be in the ER. Okay, based off of just different regulations. These are enzymes that catalyze exact opposite reactions of each other, so this is a nice way to regulate them separately. Okay, so that's another possibility. I think that's probably the more likely one, simply because all cells need to glycosylate proteins. And the glucose 6-phosphatase is really the only found in certain types of cell types. So anyway, okay. All right, so let's go ahead and end there. I don't think I need to say anything more. That gives us about 40-ish minutes, and hopefully you've got some questions. Let me go ahead and say this about the exam. The exam is going to take on the exact same format as what you see in the practice exam. If you haven't done the practice exam, do so this weekend, okay? Do it like a practice exam. Don't cheat, okay? Don't use your notes. Don't do anything. Take it for 50 minutes and see if you can get it done, okay? And the keys are posted on that as well. But the format is going to be a one matching question, okay? Then there's 5 what I would call multiple true-false questions. So these are questions, they're like multiple choice, but you have to determine if each selection underneath them is true or false. I think you did that for BC 401, right? Okay. So I prefer that testing mechanism above multiple choice, simply because multiple choice, a lot of students I find, will be able to, on a multiple choice exam, eliminate 3 of the 5 possible answers, and then a lot of times guess wrong. Okay, and then you get all those points removed and not get any credit for the 3 that you eliminated as possible wrong answers. So in this, you get credit for those possible right answers. Students hate it. I understand that. True or false is not your favorite. So you can take it out of me, I don't know, in some strange way. I don't know how, but anyway, hopefully it's not violent. But anyway, and then there will be 3 short answers. Okay, so 5 of those multiple true, false, one matching, and then 3 short answers. The short answers are worth 10 points each. Okay, make sure you allot yourself some good time on those to answer those. Okay. So questions from you. If you don't have questions, let me be real short. Yeah.
Can we go over cooperativity versus allosteric?
Yeah, okay, so the question is, can we go over cooperativity versus allostery, and really the main difference there. So let me go ahead and do this. Allostery or cooperativity, they're really extensions of one another, if you will. Okay, they're very similar, and it's sometimes hard to really see the fine line between the two of them. Okay, so let me start off this way and just say, if you have a cooperative enzyme or an allosteric enzyme, they're both going to have sigmoidal type behavior. Okay, so if we were to plot VO versus substrate concentration, let me get a little bit straighter here. There we go. If we were to plot this, okay, you get some sort of sigmoidal type curve. Okay, and that sigmoidal behavior would be quite indicative of what we would consider either cooperativity, okay, well, really cooperativity, and then allostery is an extension beyond that. Okay. The main difference here is this, that an enzyme that is just simply cooperative, okay, and doesn't have the extension of the allostery, you're not going to get anything beyond this. There's no other way to regulate it. Okay, it has 2 forms, an R state and a T state, and it will switch between those forms based off of the amount of substrate available. Okay, meaning that the substrate is inducing a conformational change in the protein. Okay. And what you see in the sigmoidal type behavior with cooperativity is really an equilibrium between that R and T state. Okay. The reason it is cooperative is because there is this capacity for it to switch between conformations. Now, in terms of metabolic regulation, these types of enzymes are really only quote-unquote regulated by substrate availability, okay? Meaning that they're pretty sensitive to changes in substrate concentration, and therefore their rate can go up or down based off of the level of substrate concentration, right? Whether that's going up or down. Now, that's cooperativity, okay? Just leave it at that. Nothing more beyond that. The extension with allostery is that you can take that enzyme, okay, and lock it or have it favor one of its states, R or T, with another molecule that would be called a regulator or an effector or a modulator. Okay, so for instance, we could say this, no modulator. And we could say this would be cooperative. Okay? Now, allostery then would be, we can extend this behavior, right, by adding a modulator. And so we'll just put, and this is kind of consistent with the diagram that I had given you, the graph that I had given you. What is being shown here is this. Now we are adding, okay, a positive modulator. Okay? And that modulator binds at a regulatory site, some other site besides the active site. And it will then, in this case, because it's positive, it's going to cause that particular enzyme to favor its R state. The language that I've used or would use would be it locks it in the R state. It doesn't truly lock it in the R state. That would indicate that there's no T state available and there's only R state. If that were true, then this would go straight to a hyperbolic curve. Okay, that's not the case. There's usually an equilibrium still. But the equilibrium will start to favor more and more of the R. Okay. Now, you can have an enzyme that's simply just cooperative, that doesn't bind to a modulator at all. Okay. And then you wouldn't have this extension of these blue curves here, right? And then we could extend this. With allostery, it can be, right, you can have that positive modulation or you can have negative modulation where it now starts to favor the T state. Okay, and this would be adding negative modulator. Favors T. Okay, and this favors R. Okay, so that's going to be the major difference between these. Now, when you think about it from a metabolic regulation standpoint, the allostery is much more useful in terms of regulating pathways because it's sensitive to not just changes in substrate, but it can be sensitive to changes in other concentrations of other molecules. Okay. And a really common one that we'll look at is a change in the concentration of like ATP that may or may not be the substrate for that particular enzyme. But it can bind somewhere else in the enzyme that's not the active site and either cause that activity to increase or decrease because ATP concentrations are fluctuating in the cell. And ATP concentrations can fluctuate in the cell and can go down because you're using it more, right? In that case, then that should be binding like enzymes that are regulating catabolic pathways and activating them. Okay, ATP won't be binding, but its breakdown products, ADP and AMP, will. Okay. So does that answer your question? Did that help out? Okay. Other questions? Yeah.
Can you go over the GLUT transporters and the absorption of glucose in the bloodstream?
Yeah, okay, so the question is, can we go over the GLUT transporters and the absorption of glucose from the bloodstream, or really maybe even excretion of glucose into the bloodstream? So there's lots to go over there. We even covered another one today, so the GLUT3. GLUT3 is got the lowest KT of them all. And let me just try and boil this down to some pretty simple things in regards to what we had talked about. So the first very simple thing would be this: the amount of transporter on the membrane. Okay. And let me go ahead and just say this. We have the liver or the pancreas, and these have a lot. lots of GLUT2. And I would also say this, always present. It's not changing, meaning there's no real, like all of a sudden GLUT2 starts to disappear from that membrane or starts to get higher in concentration. Okay, it's pretty much constant level. And because of that, then, because there's a lot of it, and this is true of transporters, this would be true of enzymes. If you have a lot of these things that catalyze these processes, then what's going to happen is it's going to reach equilibrium fairly quickly, okay, whatever it's doing. Right? And so in this case, when you have a lot of GLUT transporter in the membrane, then the rate of glucose transport from the blood into the liver and vice versa, okay, those forward and reverse processes are going to reach equilibrium. Now in the case of transport, that means there will be an equal concentration of glucose on both sides of the membrane, okay? And it'll be what we would consider equilibrated across the membrane. So if the concentration then of glucose in the bloodstream is 5 millimolar, then in the liver and the pancreas it will also be about 5 millimolar based off of this transport mechanism because there's lots of it, okay? And so that's kind of the key here, right? With this one, equal concentrations of glucose on each side of the membrane. Okay, that'd be number one. Now, compare that to skeletal muscle, and this would be the big one that we looked at. Okay, this has a changing amount of glucose, or a changing concentration of GLUT4. And it's based off of insulin, right? This is what I call insulin sensitive. Okay, so that if insulin levels spike, and the only reason that insulin levels would spike in the blood is because glucose concentrations have gone up. So right after a meal, your insulin levels will spike, assuming you had carbohydrates in that meal. Okay, and so what then will happen is that because insulin levels spike, there will start to be a spike in the amount of GLUT4 found in the membrane of these skeletal muscles. Okay. So skeletal muscles will absorb at rapid rates glucose only when concentrations of glucose in the bloodstream are real high. Okay. As insulin signaling stops, then GLUT4 will start to be sucked back into vesicles and you'll start to lose it on these membranes, which means that skeletal muscle will stop taking glucose from the blood when glucose levels in the blood are pretty low, which is good. You don't want skeletal muscles to take a bunch of glucose in low blood glucose levels. Okay, the brain needs the glucose, not the skeletal muscle. Okay. So a changing concentration of GLUT4, all right, and that means this is really sensitive to well, sensitive maybe I shouldn't say that. It's going to be, right, absorb, this is a better way to say it, absorb glucose only when in high amounts. Okay. Skeletal muscle has the ability to store lots of glucose. It stores glycogen. So everyone thinks of the liver, and we should think of the liver when we think of glycogen, but the muscle has a significant capacity to carry glycogen, okay, as well, and to make it. Okay. Now, the other thing here, this would be, so that's the two main points with the amount of it in the membrane. The other thing would be this, okay, the KT value of the transporter. And this is a concept that is a little bit more challenging to see. That's the reason I showed you that graph even the day of GLUT3, because the KT can really determine how large of changes in rate of absorption can occur. Okay, I didn't really highlight too much the skeletal muscle because it's not terribly interesting what the skeletal muscle has in terms of KT. The KT is about 5 millimolar. The big thing here would be the KT because it's so drastic. The KT of GLUT2, which is in the liver and the pancreas primarily. And it's 17 millimolar. This is about 3 times what you would find of the typical glucose concentration in the blood. Right, which means that you're sitting at physiological ranges of glucose concentration. The rate of those transporters is sitting well below 50% of their Vmax. Now, graphically speaking then, right, or mathematically speaking, again, you could just show this to yourself mathematically, you don't have to graph it, but a graph is a nice way to represent this. Okay, VO concentration of glucose here, do this here. This is really the opposite of what I started off today talking about. Vmax here. So if this is our KT, 17 millimolar. Okay, that's a KT. When we start looking here, again, my scale is a little bit hard to, this is about halfway, 4 to 8 millimolar. Okay, we have, this is 2 times, we have about 2 times. We have virtually a linear response in terms of changes in the rate of absorption. Oops, this is a millimolar, sorry. Rate of absorption versus the change in the glucose concentration in the blood. Okay, so remember it's equal on each side of the membrane, and then, okay, if for some reason the concentration of glucose in the blood jumps from 4 to 8 millimolar, then the liver and the pancreas are going to respond in a linear fashion and quickly equilibrate that, so that then the liver and the pancreas, quote unquote, know that, okay, this is the concentration of glucose in the blood, it's increasing. For the pancreas, it will respond by secreting insulin, and we'll talk about pathways that will allow it to do that. Okay, question, yeah?
So can the GLUT transporters work in both directions then?
Yes, yep, so the question is, can the GLUT transporters work in both directions? Absolutely. So that's really what we're saying, that because the amount there, and when we say it's equal, it's at equilibrium, the rate of the forward and the reverse process are identical. Okay, so they're responding according to Le Chatelier's principle. So if the concentration of glucose in the bloodstream goes up, then absorption is going to go up. Okay, in a somewhat Le Chatelier's principle type fashion. Now compare that like to neuronal tissue. The rate of absorption into neuronal tissue is usually, if not always, higher than export. Okay, neuronal tissue just is not exporting, right? Because it will trap it too very efficiently. Okay. Concentration of blood glucose in neuronal tissue is held at like 1 to 2 millimolar, okay, relative to 4 at the lowest or 8 highest. Okay. Now, neuronal tissue, that's kind of a big term, right? There's lots of cell types, so it can vary, but 1 to 2 millimolar. Other questions?
In glycolysis,
Yeah.
the reversible reactions going forward.
How do they keep them going forward?
Or do they?
Okay, so yeah, so you're in glycolysis or even gluconeogenesis, is that? Yeah, so how do they keep reversible reactions? So that would be straightforward Le Chatelier's principle. So let me go ahead and just show you this. We haven't quite gotten to regulation, but this is something that I think is important. So glucose, right? We know this. There's an irreversible step, production of glucose 6-phosphate. Okay, so ATP is used in that process. Hexokinase is our enzyme. All right. There's a reversible enzyme, phosphohexosisomerase, that will isomerize this to fructose 6-phosphate. Oops, P. There we go. And then there will be another irreversible step, more HCP hydrolysis, PFK1 as our enzyme. Okay? And this will make fructose 1,6-bisphosphate. And then you could draw, I mean, this is really simplistic way of thinking about this, but you could draw it like this. It's several reversible steps after that, right? So essentially everything until the end of the pathway is reversible. So, you know, if we think about this just from strictly a regulatory standpoint, if this is getting a green light and this is getting a green light, okay, meaning we're increasing rates of those for whatever reason and however, we haven't talked about how. But what will happen then is this will start to increase in level, right? According to Le Chatelier's principle, that will shift in this direction and that will start to increase. Okay, the rate of this is in terms of production of fructose 1,6-phosphate has gone up. So if this goes up, then this entire pathway is going to shift in this direction. Okay, and this will go up. So when you think about a reversible reaction, how is it kept going in the forward direction? It's based off of just Le Chatelier's principle. Is its reactant being produced in the cellular environment? If so, then it's going to go in the forward direction. If not, then it will kind of sit at equilibrium, or it's very possible, and this would be gluconeogenesis, right? Gluconeogenesis can do this in the liver cell. It can actually cause this to increase. Okay, regulate pyruvate carboxylase and PepCK, the first two steps of gluconeogenesis. That will cause that to go up. That will shift this entire thing in this direction. Okay, that will cause this to go up. Now you have to have a bypass. Okay, there, FBPase1. That will cause this to go up. That will shift in this direction. And then you have to have a bypass here. Okay, and those have to be regulated. This bypass here, and there's one that's implied over at the end. Those have to be regulated in a differential manner than the regulation of glycolysis. Okay, but those things can just respond based off of what regulation is happening at the top of the pathway, either one of these pathways. Yeah.
Are the enzymes that are involved in the irreversible steps, are they cooperative enzymes?
Okay, so the question is, are the enzymes involved in the irreversible steps cooperative enzymes? So specifically, hexokinase, PFK1, and pyruvate kinase, I would have to look at those specifically. I don't think so. They're much more sensitive to allosteric regulation. Okay, they may be cooperative, but their level of cooperativity is not really what is the tail, quote unquote, that wags the dog. In other words, they're not waiting on substrate availability to change their rate. Okay, they're more sensitive to allosteric regulation. Hexokinase might be the exception to that, though it's kind of strange in terms of how it's regulated. Okay, yeah. So, other questions? Lecture 5 will be regulation. So we're going to look at how this is done. We'll talk about it from a tissue standpoint. We'll look at the major features of it. How. Yeah. So, and you'll see allostery is really the thing that does it. Yep.
Does lactate fermentation run only in anaerobic conditions, or can it run when it's not?
Yeah, okay, so the question is, does lactate fermentation only run in anaerobic conditions? The answer is a resounding no. So it can definitely run in aerobic conditions. There are lots of documented tissues that even in supplied oxygen, blood supply, they will run lactate fermentation. Okay, and they will excrete lactate, or they will use lactate for metabolic need. Okay, yeah. Lactate metabolism at one point in time was thought to, okay, it's just really kind of this anaerobic side effect. Lactate will be produced in large quantities by the skeletal muscle. It will be excreted by the skeletal muscle, absorbed by the liver, and made into sugar again, glucose. But that model has been abandoned 20 years ago. So, although it's still taught in that way in some ways. So, we typically introduce it as an anaerobic pathway. Okay. Other questions? You got me for like 15 more minutes.
From the homework? What
Yeah.
was the logic for using, well, it's not from homework, the two different pathways for removing the NADH across the membrane?
Oh yeah, okay, so are you talking about the malate aspartate shuttle and the glycerol 3-phosphate shuttle. What's the logic behind that? Okay, so the question really, if you didn't hear it, what's the logic behind having two different mechanisms to move NADH across the membrane? It actually has, I don't know if I can't remember if I highlighted this or not. There's actually a tissue distribution or preference for those two. Okay, so the glycerol 3-phosphate shuttle is found in primarily skeletal muscle, and I believe it's the brain that it does that. Okay, so and then the other one, the malate aspartate shuttle, is found in larger quantities in the liver, cardiac tissue, and the kidney. So there may be some capacity of the liver, let's say, to run glycerol 3-phosphate shuttle, but not nearly as much. Okay, so when we start to talk about these tissue distributions, what you're really looking at is the levels of expression of the enzymes found in the shuttles. Okay, and you can have differential expression of those different enzymes in different tissues. Okay, they're regulated differently at a genetic level, and because of that, then there will be one tissue that has more malate aspartate, preference for malate aspartate shuttle than the other. Okay. Now your next question is why? That's a great question. Because. So sometimes it's really difficult to answer questions like that simply because it's what we observe. There's probably logical explanations to it, some of which I'm ignorant to for sure, some of which the entire field is ignorant to. So, yeah.
Can you briefly go over the Hill coefficient?
Yeah, okay, so the Hill coefficient, this is actually kind of going back to our original question here, cooperativity. The Hill coefficient is something that we use to define the level of cooperativity, okay? And what I would, the take-home message for you of the Hill coefficient is this, okay? Let's do this, take home. Okay, a Hill of 1. This means no cooperativity. That's essentially a Michaelis-Menten enzyme. It will not exhibit sigmoidal behavior. There is no conformational change. And in this case, I remember this number. It takes an 81-fold change in substrate concentration to change rate from 10% Vmax to 90% Vmax. Okay. Now, you can then go up in number from there. 2, 3, there can be, right, fractions of those numbers as well in terms of that. But Hill coefficient of 2 will be some level of cooperativity, a lower level of cooperativity, but this would be cooperative. And I can't remember the exact fold change. I think it's like 9-fold. Don't quote me on that. There's a table in the notes, but it's about a 9-fold change in substrate concentration to change rate from 10% Vmax to 90%. And the amount of change in the concentration of substrate as your Hill coefficient goes up, the amount of change that you need to go from 10% to 90% goes down. Okay, I think it's like at a Hill coefficient of 4, it's like 4 millimolar or 4-fold change. Okay, so you become essentially the cooperative enzyme becomes more and more sensitive to smaller changes in substrate concentration. Okay, more cooperative. Yeah, let's just leave it at that. Yeah.
So the ones below 1, does that mean that it would be inhibited, so you would need more of the
Yeah.
substrate?
Yeah, so yeah, it's really strange. Negative cooperativity, now I can't think of an enzyme that is negatively cooperative. Okay, but it has been observed. But if you have a Hill coefficient below 1, then and this is a strange thing to say, it's really being inhibited by its substrate, okay, which seems weird, okay. And so I don't know an enzyme, nor do I know why that would be the case, why you need something like that. But I think like the fold change there is like, yeah, it just goes up. It takes more than 81 fold change in substrate concentration to get the 10 to 90. Okay. Yeah. Weird.
Is there any relationship between Hill coefficient and KT?
Okay, so the question is there any relationship between the Hill coefficient and the KT? I'd have to go back and I'd have to look. So, yeah. Other questions? No? Okay, well, we only got about 5 minutes left anyway, so how about we do this? We'll just stop right there because it doesn't seem like there's a lot of other questions. And if you have questions, I can hang out for about five or so minutes. And if you want to walk back with me to my office, I can even do that. But once I get there, I got to leave. So, okay, so I will see you on Monday. Come ready. Try and be here early. I think there's a class in here on Monday, unfortunately, but we'll try and get you in and get it handed out as quickly as possible, okay?